it's very openly described on the developer page that we have, and is a part of the software stack, a very important part as shown here on the slide. The graph analyzer gives you visibility into what's happening on the IPU side, on the accelerator, while System Analyzer is the counterpart, giving you the visibility into what's happening on the CPU, with the goal of you as an engineer being able to see bottlenecks and inefficiencies in maybe an implementation of an operation, or on the CPU side, maybe the data loader takes significant time and is a bottleneck to unlock performance of a model on the IPU. So you can download the both PopVisionTools from the downloads page. There is no login required. There is a nice video and of course an extensive document describing how to use that. And there is a nice help in the graph analyzer and system analyzer themselves that help you get started, create first profiles and analyze those. Creating a profile looks something like this. So in this case, I'm running in a virtual environment on a tutorial, PyTorch basics. The program, the Python script that I'm running is this walkthrough. So the final implementation of the tutorial in this case. And what I did to make Poplar output the profile is add this environmental variable, Poplar engine options. And specifically in this dictionary of options, I have set autoreport.all to true. And then I have pointed to the directory that the profiler needs to create to save the report. And I also want to allow out of memory compilations to still produce a profile so that I can at least analyze which tiles and which program steps lead to this out of memory situation. And well, then you just execute it normally. And after that, you will have this report directory created on your machine. The graph analyzer has several tabs on the left. There will be a summary, which shows some high-level overview numbers of the graphs of the execution traces that you are analyzing. Memory report is one of the tabs that can be very interesting when something does not fit, or you want to see if you have a lot of room to maybe fit more items in your patches or make the layers larger. On this chart, on the horizontal axis, we show the tiles that are available in the IPU. So in this case, it's just one IPU, so tiles are numbered from 1 to 1471. And then the memory used by the program is shown here based on, well, on the memory used in each tile. And then if you select a specific tile, you will see a lot of details of the memory allocations here. And you can dive into slices of this data with how much memory is used by the compute sets, vertices, exchanges, and variables on this tile. The next tab is the liveness report. And in this case, on the x-axis, you have program steps. And these are basically the BSP steps the graph of the engine that the compiler produced. Again, at the popular C++ level, you have control over what's included in every compute set, in every program step. If you program in TensorFlow or PyTorch, these come from the compilation lowering procedure. And with this, you can analyze how much memory is consumed by the program during each step with, again, some details being available here below. And the typical scenario for using these two memory reports is when you see that you are running out of memory for model of interest, you can produce these graphs, these profiles, and see if there is a specific operation that runs out of that memory. Is there a way maybe to modify it, maybe to do some in-place operations, maybe to serialize matmals or serialize the batch computations in this model, maybe split those between more than one IPU and run in a pipeline instead of running on just one IPU, which we do for bird-sized models, for example. Sorry. The next tab of
question on the chart window, Alex.
Right.
From Michael.
What happens on the chart between 400 and 500 steps? Okay, what's happening there? I actually do not know, but it would be interesting to see. Let me try maybe to open that report. But yeah, this is a very valid question. Which report is that? So this is report training. Let me try and open it. What I like about these tools is that it's typically quite insightful to actually look at those traces, and it reveals these steps that can look suspicious. So this is apparently some operations that do not consume a lot of memory, but still are counted as program steps. And it can be the case that these do not take a lot of cycles, and for the cycles, I need to switch to this execution trace instead. But well, program steps can be very short in time, so it doesn't. Seeing this as an absence of activity is not necessarily true. These are just some operations that do not require non-always live memory. And you can add and see always live memory here. And always live memory would be weights or some other things that are used throughout the execution of the model. So you can see when I turned on the visualization with the always live variables, then I can see that it's not zero. And these always live variables are shown here in the details section. For example, there are weights that take a significant amount of memory. There is also vertex code and other kinds of codes and some states that are significant. Overall, I should mention that this model is quite small, and out of the total 900 megabytes that we have on the processor, it only takes, well, a tiny portion. Yes, PopVision is a proprietary tool made by GraphCore, answering to Alfred, but it's free to use. So, and then the next tab that I wanted to show is this execution trace, which is providing the visibility into the execution of a graph on the IPU. You can use several ways to visualize this trace. The flame, which is quite classic now, which it is used in many other profiling tools as well. And this is basically a hierarchy of operations that make a part of the graph. And for example, this would be, let me dive in even deeper here. So this would be a group normalization operation, and there is a set of reductions and options associated with that, some multiply operations that you can, well, take a closer look at. And then if something looks suspicious, like, for example, Michael has mentioned the suspicious memory consumption between steps 400 and 500, then you can take a closer look. Question: can PopVision run on my laptop or only on GraphCore? So it is meant to be run on your laptop normally, and in the downloads section on our slide, you will see the supported operating systems for the PopVision tools. So if I click download now, I will see that we support Ubuntu, Mac, and Windows for that, and 2 versions of Mac are available for both System and Graph Analyzer. There is an option to run it remotely with the X11 protocol, but I would say I prefer to run it locally. And then with that, I can open reports remotely. For example, this report, as you can see, is taken from a remote machine. I have SSH access to that machine, so when opening a report, I can just say I want to open a report on a remote machine. I will provide my username that I use for SSH, and I can use that SSH port, which is default, or I can edit it here. And I can connect to that machine and navigate to choose the right directory that contains the report of interest. That's the typical way that I think is convenient to use with these analyzer tools. And thank you very much for the questions. It's very nice to see those coming up. A way to get even more transparency into what's happening during execution is to visualize this BSP trace, bulk synchronous parallel trace. In this trace, again, on the x-axis, you have cycles of execution, and on the y-axis, you have tiles that run a set of codelets. In this case, the red color is the execution of compute vertices. The blue color is exchanges, and then the yellow color is waiting for synchronization. So you can see in case of this small model, there is a lot of synchronization. Not all of the tiles are used for all the operations. For example, for this set of operations that are related to the loss computation, many tiles appear to be waiting for synchronization, not running a codelet, which can, for us, can mean that we can maybe use a larger batch size for this operation. And this is the way you enable the BSP trace here. And you can use the options button to visualize the execution trace in different ways. You can show, well, different helpful objects there on the execution trace. So this is the graph analyzer, which helps on the IPU side, and a few tutorials that involve the graph analyzer are shown here. The first two links, I should say. So this one would be comparing two profiles with an optimization and without an optimization. Recent comparisons. I think I can try to show it again. The mode where we compare two reports is very useful because you can see how the execution changed between the two runs of a program, of a model. Maybe the number of compute sets has changed, number of edges in the graph, number of variables. And then you can visualize memory reports side by side. In this case, this is identical in terms of memory consumption, but the execution traces will be different. This will show that the overhead of moving data to the IPU is smaller versus this case. So this, for example, this execution was done with device iterations equal to a large number, maybe 10, and this one, device iterations 1, which means that during an engine run, you have only one execution of the computational graph there, and then there is a large overhead when starting the engine once again. In this case, the overhead is smaller. And there are more best practices that you can enable to reduce this overhead even more. For example, if your computation is significant, takes a good number of cycles, then you can overlap this stream copy, which moves data. Well, it shows that the data is being moved from the host to the IPU, maybe a next batch is coming in, as in this case, and also getting the results back to the IPU. You can overlap these communications with the computation on the IPU. So there is a concept of I/O tiles, as we call it, and it is described in the optimization documentation that I will show later today during the best practices section. So question, how can we optimize a model if we see a lot of synchronization time in the chart? So if you are seeing a lot of synchronization time in the chart, as we have seen here, that probably means that the compiler was not able to distribute an operation in the sequence of operations in the computational graph evenly or reasonably across all the tiles that are available on the IPU. That means either that the amount of work is not enough to efficiently parallelize it, and that would mean that the compiler thought of using more than one tile, and it decided that the overhead of the communication will be larger versus just using a small number of tiles, as in this case. What can you do potentially to optimize that is well, if it's at all possible, if there is enough work for that, and the compiler is wrong, then you can either create a custom operation for that, or you can point to that to us, because we think we try to optimize the Poplar libraries as much as we could, but maybe it's not always the case. So please feel free to let us know. If you are programming at the Poplar level in C++, then that would mean that you did not put a compute vertex or 6 compute vertices on a given tile or set of tiles. So they are just waiting there doing, well, power saving, which may not be the thing that you want them to do. So you have a lot of control and flexibility at the Poplar level. Thank you for the question. Great question. And the last thing that I wanted to show today during this talk is the system analyzer. There is a tutorial on that shows, well, guides you step by step how to use it. And System Analyzer produces visualizations like this, for example, where you have time, and this is wall clock time in this case, as your program runs, associated with the operations that are executed on the on the CPU, sorry, this is the CPU side tool. So on the host side at a given time. So it tracks entries and exits of functions of interest, and you can mark specific events of interest, and the System Analyzer will save those time steps and visualize those on a chart like this. And you can not only include the time related, like the moments of start and stop of different functions, and not only keep track of the hierarchy of those calls, but you can also visualize values such as board temperature, or maybe accuracy of your model. You can use System Analyzer to visualize those as well on the time chart, in addition to the execution related stuff. And another interesting function that many people find useful is heat maps for the distributions of values in specific tensors that you find interesting. And a typical use case for these is tracking the distributions of weights in neural networks, neural network layers. As the model trains, for example, you can see that in this case, the epochs are shown here underneath the heat maps. The bubbles here show the moments of when an epoch begins. So the distribution of the weights during the first epoch is quite different, and it changes as the training goes on. And during the epoch number 9, in this case, we can see that there is kind of the bulk of the values falling into this space on the histogram, while there is some kind of set of well, outliers, separate mode in the histogram that wants to stay separate for some reason. So I guess this is the main part of the talk. And again, I would invite you to refer to the tutorials there that describe these two tools, as well as everything else. And in each of the tools, you will find nice help section that will help you understand, well, how to start, what to do, how to produce those profiles, etc. And I can probably also show an example of me running this profiling with the goal to produce the profile for the system analyzer, which is enabled by adding this environment variable PVTI options. It's also a dictionary with the enable equal to true, and then directory equals to the target directory where I want to see my report. So, and then it executes the program and it outputs the profile to a specific directory, reports in this case. And it will look something like this with one large file, which is the file of interest, and a bunch of helper files that track some minor events there. Yeah, I think this is it for this section. I'm happy to answer any questions. And again, yeah, the call to action is to please consider joining the allocation program on Argonne in ALCF, and then Graph community is there.